So we started off with tutorial 3, NFA, DFA in the last week's lecture class, and we just discussed about the example problem. It says give a regular expression and an equal NFA for the language over A or B that starts with AA and contains the substring BA. Convert the NFA you obtain to a DFA. So there are two parts for this question. So first part states give a regular expression, and second part states first part says give a regular expression and an equal in NFA. Second part second part of the question states convert the NFA you obtain to a DFA. So first thing first, we have to write the regular expression. So I explained that what the language specification says is the language is made up of the alphabets A or B. So essentially simple, the alphabet set is A or B. Okay? And what is the pattern of string? The pattern of string that this language produces is the string starts with AA and contains the substring BA. Substring means part of the string is BA. So the pattern goes like this. The string starts with AA and there is a substring BA that is part of the string. Okay? Subset. So between this AA and BA, we can have any combination of A or B. And after this BA also, we can have any combination of A or B. And some of you may have a question, why should I have an A or B here and A or B here? Can I have an A or B here? Cannot. Because the question clearly says the string must start with an A. And somewhere in the string, as part of the string, we should have a BA. So between this A and BA, we can have any combination of A or B, don't care. And after this BA also, we can have any combination of A or B. So this is the regular expression. Okay? So this is where we stop. And so I'm going to show you how to construct the NFA for this. So NFA stands for non-deterministic finite automator. Non-deterministic finite automator. And deterministic stands for deterministic finite automator. So why we call it as non-deterministic finite automator, deterministic automator, we will understand once we discuss the answer. Okay? So we are going to construct the NFA and DFA in terms of a state diagram. Okay? So recall, I have said that these bubbles or these circles represent state. Okay? So each state is going to have some process. It's going to do some process. Okay? So here, each state will accept some input alphabet and it will process it. Okay? And these arrows are called as transition. Okay? Transition means you move from one state to another state. Okay? Transition means change of state. Okay? So when you move from Q0 to Q1, so you have an arrow line here. This is not transition. Okay? Change state from Q0 to Q1. So when this machine will change state from Q0 to Q1 for the input A. If you go and input alphabet A, the machine will transit, go from Q0 to Q1. Okay. And same thing goes with Q1 to Q2. So between Q1 and Q2, you can see there is an A again. So meaning, if we give an input A to Q1, the machine will transit this change state from Q1 to Q2. At Q2, we have a loop back here. So at Q2, if we give an input A, it doesn't mean the machine goes through this. What this means is there is no change of state. The machine will remain at the same state. Okay? If we give an input A, the machine will remain at the same state. Okay? But there is a choice if we give input as B. So B means the machine can remain at the same state. That's what this looping back means. or the machine can move from Q2 to Q3. There could be a change of state. Okay. So the machine can transit from Q2 to Q3, or the machine can remain at the same state. This is just to understand the transitions. Okay. This arrow here denotes that Q0 is a start state. So meaning the inputs will be initially fed here. This is where the machine will start accepting the input. Okay. So a bubble with this arrow means it is a start state. We can also represent like this, simply like this, an angular bracket, or you can put an arrow. So this means a start state. Okay. So Q0 is a start state. Q1, Q2, Q3 are intermediary states in the middle. And Q4, you can see a double circle. Okay. So when you put a double circle, it means the final state. Okay. So a bubble with a single-headed arrow like this is a start state. These all are intermediate state, and a bubble a state with two circles is called as the final state. Okay. So with this understanding, let's go through how to construct the NFA for this. Okay. I'm going to draw and show you. So observe me carefully. NFA, DFA is one of the easiest topic in theory of computation. Okay, very easy to construct the NFA and then convert to a DFA. Okay. So I am looking at the regular expression. So you have example strings here. Okay. So this part of the regular expression is compulsory, and this part is also compulsory. Okay. So when these two connect takes a value 0, we will end up with AABA. That's what we discussed in the last class. Right? And I also said when this star takes a value 0, not necessarily this star should also take a value 0. Okay, they can take different values. When this star takes a value 0, this can take a value 1 or 2 or 3, anything. Similarly, when this star takes some value, this can stay at 0. Okay, or this star can remain at a particular value and this keep on changing. Or this may remain at a particular value and this keep on changing. So to me, these two stars can take different values. They need not necessarily take the same value. Can they take the same value? Yes, they can take the same value as well. Okay. So to me, they can independently change. Okay. So if I take both the stars to take the value 0, then this part of the substring will become empty string. This part of the substring will also become empty string. So you end up with AABA, and that's what I showed you. Okay. So what happens if this star takes a value 1? So AA. So when this star takes a value 1, we can have either A or B, because the string is made up of A or B, but length is only one character because star is 1, right? So I can have A. That's what I showed here. A, and this follows BA. I've taken this star to take a value 0. So when this is 1, not necessarily I need to have an A, I can also have a B. Okay. So that scenario I've given here. AA, star takes a value 1, so I will have a B. Oh. Okay, I've taken a different value here. I've taken this star to be 0, so I have AA, and this BA is here, and this star to be 1. So I've taken B. So AA, BA, B. Explain one more time. We have AA here. I've taken this star to take a value 0. So this BA will remain, this BA remains. And I've taken this star to take a value 1. So I've taken B for a change. Okay, you can also have AA, BA, if this is 1. Okay. So you can have different possible combination of strings. Okay. So let's see how to construct this machine. Let me hide this so that you don't get distracted looking at the answer. So I'm going to draw and show you how I'm going to construct the machine. So here, life is easy because there is a regular expression. So very fast I can draw the NFA. Okay, the diagram you saw is called as state diagram or state transition diagram. Okay. So we need to start with AA, right? So I need to process AA. So you see how I'm going to do, huh? So I label this as a start state. You can even put like this, no harm. A single headed arrow. Then I'm going to process A here. I need to have two A's. So I force the machine to go through two A's. Okay, I force the machine to go through two A's. Huh? Yeah. And then what we are going to have after AA, I hide this. Must is BA. I also hide this. Why I am hiding this means if this takes a value 0, this also takes a value 0. This part of the string will become empty. This part of the string also will become empty. You will have only AABA. That is this scenario, AABA. So before the machine halts, it should have seen BA. Okay, before the machine halts, it should have seen BA. So I'm going to process that next. So I put B here. I put A here. I make this as a final string. So, if I take the smallest possible string, AABA, so what happens if I give AABA as input? Okay. So, first letter is A, right? So, A will be processed. So, I'm going to label the states. You can even label like this, no harm. Labeling is like we have names. Why we have names? To identify us, to call us. Okay, even venue, our room also has a name, right? We don't say, hey, go to floor level 6 in block E, and after you exit the lift, turn right, you occupy the last but second room. Right? It's very difficult, you know. Instead, hey, your class for 12 to 1 is at E602, self-restraints, block E level 6, room number 2. Like we have names to be called, right? So likewise, this labeling is to refer to these states. Easy to refer. Okay? Instead of saying first state, second state, third state, fourth state, and fifth state, easy to remember. Okay? So we are labeling in terms of Q. Why we are using the letter Q means it's mathematical. Okay? So in set theory, normally set of states are labeled as Q. It's a definition. So I am labeling this as Q0, Q1, Q2, Q3, and Q4. So, state Q0 is the start state. Okay? State Q0 is the start state because I have labeled like this. So, it's the start state. So, when I give A, the machine transits from Q0 to Q1. Okay? And the next letter is again an A. So, when we give an A as input to Q1, the machine transits from Q1 to Q2. The next letter is B, then is A. So when you give B as input to Q2, the machine transits from Q2 to Q3. When we give A as an input, the machine changes state from Q3 to Q4. Okay? No more characters to be processed. Okay? No more characters to be processed. Okay? And the machine has reached the final state, halt and accept. Okay? So it's a valid string, so the machine halts and accepts. I also told you during lecture, why we go for NFA DFA in the sense, after constructing grammar, okay, for a given language specification, we want to realize it. Realize it means we want to implement and see how it goes. That's what we're doing with the help of NFA DFA. Okay. So basically, this is an automated. Okay. Automata means plural. Automated means singular. Something like data and data. When you say data, it is plural. Okay. And when we say data, it is singular. Very seldom we use the word data. We always use the word data, right? Database, set of data, data set. So similarly here, automated means singular, one machine. Automata means plural, machines. Okay. So this is an abstract machine or a mathematical machine to see how a string is processed for a given language specification. Okay. So we have processed this string. Okay. So now how to process these strings? So what we did was we took this as 0 and this as 0. So this becomes empty string, this becomes empty string. So we looked at AA and BA here of the regular expression. So between this A and BA, we can have any combination of A or B. We can have any combination of A or B. So what I'm going to do is after AA, right, I'm and before the BA, we can have any combination of A or B. After the AA and before the BA, we can have any combination of A or B. This is something like a bypass route. Okay, you can simply bypass this. Okay, if Pranay star takes a value 0. Okay, if Pranay star takes a value 1, after AA is given here, after AA, we can have either A or B if this takes a value 1. So I have taken the scenario when this is 1, I am taking this AAA, and then BA. Not necessarily, we can also have AAB, then BA. Okay? And after BA, whatever follows depends on this value. If it is 0, this part of string will become empty. That's what I have done here. So I take this as 1, AAA, followed by BA. I have taken this as 0. Okay? So this part of the regular expression will be taken care by this, and similarly we have an A or B combination after the BA. So that is after BA. After BA is here. Sorry, I put it here. A or B. So let's process this AAA BA. Right? First A, I write it here so that you can visualize it better. For the first A, the machine transits from Q0 to Q1. The machine is at Q1 now. At Q1 now, A has been processed. Now the second input is A. So at Q1, right, you have to follow carefully, otherwise you may have difficulty in understanding. So what people think is, they think like this, like a train, you give A, B, A. And sometimes students come and ask me, is it not this A goes first? And how do you see this? How do you say this A goes first? You get me? This is not wrong. Right? If you don't listen to me, then hey, you say input, triple A, B is given as input. This is how it should be given as input. So if this is how the input string is given here as input, then should not this A be processed first? Because this appears first to it, right? Okay. So we read from left to right. I don't know whether this was discussed in your computer architecture and organization, right? How do processors, read and process strings? Processors means I mean microprocessors. Okay. So how do Intel processors process strings, and how do Mac processors process strings? Okay. So Intel processors, they process from left to right. Okay, let us not go there because I don't know whether it was discussed or not. But to make life easy, so here what happens is, this is the first letter. Maybe I write it bigger. This is your input string. I'm looking at this string. So this is the letter that is given as input here. Okay? Okay, yeah? This is the input string, no doubt about it. But this machine processes this A first. Okay? So when this A is given as input here, okay? So what is the instruction here? A means you transit from Q0 to Q1. So where the machine is now? Where the machine is at? Which state? At Q1. Okay? So what is the next input? A. So next input does not go here. The machine is at here now. So this A goes as input to Q1. The instruction here is A means you transit from Q1 to Q2. Now the machine is at Q2. So next input is A. When it is A, the machine has no choice. It has to go through this. Now this is for B. Okay, A means no choice. The machine has to go through this. Okay, it means the machine stays at the same state. There is no transition. There is no change in state. Okay, it goes through this, and the machine stays at the same state. Okay, now the machine is Q2. At Q2, the input is a B. At Q2, when the input is a B, there is a choice. Meaning there are two routes. Okay, this route or this route. Okay, listen to me carefully. So I am going to explain non-deterministic now. Non-determinism now. If when the input is a B, I have a choice, or better, the machine has a choice. It can take this route or it can take this route. Okay? What if the machine takes this route for B? The machine transits from Q2 to Q3. The machine is at Q3 now. Next input is A. A means instruction is transit from Q3 to Q4. Entire string has been processed. Machine is at the final state. Halt and accept. Okay. Now I am going to slightly reverse or roll back. I go back here. Okay. The machine is at Q2 and I have input B. The machine has input B. So I took this route. Now I am going to take this route. So what happens is the machine takes this route. When the machine takes this route, so B means the machine remains in the same state. No state change. B has been processed. So next input is A. When the next input is A, the machine has no choice. This is for B. Right? A means the machine will remain the same state. Entire string has been processed, meaning no more alphabets or characters to be processed. Okay? The machine has processed the string. Okay? The machine is at Q2. This is called as halt and reject. Because when there is a final state, okay, the machine should halt only at the final state after processing the string. Okay? If the machine halts at any other state, it is called as halt and reject. If it halts here, it is halt and accept. So for this is actually a valid string. Okay? For this valid string, there are two scenarios. One scenario is halt and accept, another scenario is halt and reject. Okay? So why this happens? This happens because there is a choice for B. Okay? So we call this as redundancy. Redundancy means duplicate. Okay? So there is a duplicate route for B. Or in terms of decision making, there is a choice for B. Okay? So if the machine chooses this route for B, it leads to halt and accept. When it leads to success. Okay? If the machine follows this route for B, then it leads to a failure, halt and reject. The string is a valid string. Okay? So now a question arises: how the machine will know that this is the correct route and this is a wrong route? The machine does not know. Okay? Unless we put intelligence into this machine. Okay? Unless we put intelligence into this machine does not know which route leads to success and which route will lead to failure for a valid string. And we call this as non-determinism. Okay? And that's why this machine is non-deterministic. Okay? For a valid string, so I'm going to explain now. I'm going to summarize now. For a valid string, there could be more than one route. Okay? Some routes could lead to success and some routes could lead to failure. Okay? So how the machine will know which route leads to success and which route leads to failure? The machine does not know. The machine cannot determine. Okay? The machine cannot determine which route leads to success and which route will lead to failure. That's why we say non-deterministic. The machine cannot determine by itself. The machine cannot determine by itself which route will lead to success and which route will lead to failure. Okay? So we call this as non-determinism. Hence only this machine is an NFA, non-deterministic finite automaton. So what is the cause of non-determinism? Choice. Right? If there is a choice, we call it redundancy. If there is a choice or redundancy, it leads to non-determinism. So we know what is the cause of the problem, right? Problem solving in general, right? We know what is the cause of the problem here. So if we can remove this cause, you can solve it. What we can solve it? We can solve non-determinism. So to solve non-determinism, we have to remove redundancy. One condition. There is one more condition. Every state must have an outgoing arrow for every input alphabet. So there are two conditions. I've also given that in the tutorial because I know I say in the class definitely after some time you will forget. Okay, that is the natural beauty of the brain. Brain cannot remember everything that it hears. Okay, if we can remember everything, we all will go mad one day. Okay, so it's naturally it is created by God like that. Certain things we forget, certain things we remember. Even when we are a child, we remember. Even now you recall, certain things you remember what happened when you were a child. Not everything. Okay. Something recently happened, you would have forgotten. Something happened many years back, you still remember. Okay. I still remember how my handwriting used to be very ugly. But later, now no. But it used to be very ugly. Okay. I start here, I end up here. Or I start here, I end up here. Okay, it's never in straight lines, and beautiful. So I still remember when I was that time, my time, standard 2. I had a teacher, an Anglo-Indian, an Australian by name Rose. Okay. So she taught us, not only me, she taught the entire class how to write. Okay. So when we write, she will say, after you write a word, you place your little finger here on your own book to give a space in between words. Okay? And then the next word. Place the finger again. The next word. Okay? And she also taught us, why I'm saying this means, it happens to most of us. This is natural beauty of the brain. Certain things happened in, when we were a kid, we remember. Certain things just happened, Today morning, I took the Federal Highway. Did I notice crossing PJ Hilton on the left side and Sheraton on the right side? I don't remember. Okay. A lot of times it happens, we don't even remember we have passed by certain landmarks because the final destination has been programmed here, Lakeside campus. That's all. Right? Certain things we remember, certain things we don't remember. Now, let us come back. Let us not go there. We get drifted. What I'm trying to say is, if we can remove this cause, one cause is redundancy and leads to non-integration. Okay. So there are two conditions I have given here. A state must not have any redundancies. This is what I showed you just now. Another condition is every state must have an outgoing arrow for every input alphabet. If you observe here, what we have constructed is an NFA. Okay? What we have constructed is an NFA here. So what you see here exactly. Okay, but I want to show you how I drew this. If I explain with the answer, you won't understand. Hey, how did you create this? This question will come. So I've shown you how I created, or better, how I constructed this machine with the help of a state transition diagram. Okay. So I need to remove the redundancy, and I need to ensure every state has an outgoing arrow for every input alphabet. If you observe this NFA, Q0 has an outgoing arrow for A. There is no outgoing arrow for B here. Okay? So, first condition says every state must have an outgoing arrow for every input alphabet. For this machine, there are only two input alphabets. They are essentially A or B. Is given here. A or B are the input alphabets. So at Q0, I have an outgoing arrow for A, there is no outgoing arrow for B. At Q1, I have an outgoing arrow for A, I don't have an outgoing arrow for B. Right? At Q2, I have an outgoing arrow for A, but I have redundancy for B. Redundancy for B. So I should remove one of these two fellows. Okay? At Q3, I have an outgoing arrow for A, no outgoing arrow for B. Okay? At Q4, no issue. I have an outgoing arrow for A, I also have an outgoing arrow for B. Okay? So this is same as drawing like this. Okay? You have an outgoing arrow for A, you also have an outgoing arrow for B. Okay? When you have two alphabets, you draw like this is okay. Okay? Later you will see we may use 10 alphabets. 10 alphabets means 10 arrows. It becomes very cluttery. Okay? Very cluttery. Doesn't look nice. Okay? So we simply say you put A or B. So meaning This loop back is for both A as well as B. Okay? Means the same. Okay? So now we are going to convert this NFA into a DFA. Observe me carefully. Very easy. Very fast we can do. I'm just going to apply the two conditions. Okay? So first condition is every state must have an outgoing arrow for every input alphabet, right? Every input alphabet, right? So Q0 has an outgoing arrow for A, but does not has an outgoing arrow for B. Okay? So I'm going to take an arrow for B. Okay? But I'm going to take the arrow for B to an error state. I simply label it as E, meaning error state. Okay? So you may ask why you take it for error state. Will every machine will have an error state? No. Every machine may not have an error state. Why I am taking this B to the error state means, what does the question says? The question says that the string starts with AA. So the string should start with AA. I cannot start the string with a B. If I start the string with a B, it is invalid, right? So I take the B to E, error state. Okay. So now Q0 has an outgoing error for A as well as for B. Okay. Condition 1, huh? So at Q1, I have an outgoing error for A. I don't have an outgoing error for B. So what I do? Again, I take it to error state. Why I take it to error state? Because again, the question says the string must start with an AA. So we cannot start with B. Okay. Second letter also cannot be a B. First two letters has to be A. So I take the B here to here. So why I do this? I want to satisfy this condition. Every state must have an outgoing arrow for every input alphabet. So Q0 should have an outgoing arrow for A as well as for B. So A means is valid, B means invalid, so I take the error state. Here again, A means is valid, B means invalid, so I take the error state. Okay? And here, I give a loop back and I label it as A or B. So why I do this in the sense, this condition says every state. Every state. Okay? So error state is also a state. Okay? So theoretically, this state should also have an outgoing arrow for every input alphabet. So I give an arrow for every input alphabet here to satisfy the theoretical condition. Understood? Now, we are at Q2 now. Q2 has an outgoing arrow for A, no issue. Right? But B, there is a choice. So we have to remove one of these two fellas. Which one to remove? This B. Why means the question says after AA, before we halt, before we end, that is the final state, we have to process BA. So we cannot afford to remove this, right? But we can remove this. Okay, we remove this. So Q2 has outgoing error for A, outgoing error for B, fine. Right, it's fine. Right, but we have to be careful. See this pattern of string. This pattern of string. So I can have a string that starts with AA. And before the BA, I have A or B Tene star, right? Right? So what happens if my Tene star is a 2 or better a 3? If my Tene star takes a value 2 or 3, right? So let me show here. I am taking this value to be 3, for example. After this, we have to have a BA, and after this, we can have a A or B, and star. Let me take this as 0, so that my string is small. Okay. So what will be the string? AA. When this is 3, I can have this 3 means I can have 3A. Okay. I can have triple B. I can have okay. You understand? So this part, as far as it has 3 letters, it is fine. It can be any combination of A or B. Okay. So I'm going to show you 2 combinations. This is mandatory, this here. I can have something like this, followed by DA, right? This combination, no issue. I'll show you. First A, no choice, huh? This is for B. So A means it goes here. This A means it goes here. This A means, correct, right? So all these A's, these three A's will be processed here. First A, second A, 3A, B, A. All in answer, no issue. Okay. I'm going to change the scenario. A, so B means B, A. Once I'm here, I don't need to think about it. It will be taken care by this, B, A. Understood? Okay. So what happens? This is mandatory this year. A, first B, first B, second B. There is no outgoing error for B here. You understand? So the machine will halt here. It doesn't know how to process this B. Why it doesn't know how to process this B? There is no instruction how to process B here. So the machine will halt here. But this is a valid string. Halt and reject cannot. Okay, it has to be processed. So why this happens? Because we removed the B here. Right? This B actually took care of this situation, but since we removed because of redundancy, right? So we are stuck. So how to improvise this? So I have to loop back. Loop it here, or loop it here. Loop it back, huh? Sorry? Loop back to? Loop back to 3. Loop it here. Yeah. When you loop it here, or you loop it here, right? This state will have an outgoing error for A and an outgoing error for B. If you loop like this. If you loop like this state will have an outgoing error for A, outgoing error for B. Meaning, you are trying to satisfy this condition. Every state must have an outgoing error for every input alphabet. Okay? By having an outgoing error for B. But why I left a gap here in the sense, we have to decide whether we have to loop it here like this or loop it like this. Either one only, yeah? Yeah. So you have to check, Yeah. One of this looping will work. One of this looping will not work. Right? So what happens if I have 2B? So A, no issue. First A, second A. So this B means it goes here, no choice. For this B, if I loop it here, it comes here. For this B, again if I loop it here, it comes here. For this A, I land here, no issue. All on that side. Okay? So what happens if I use this loop for B? So first B it goes here, second B it comes here, third B it goes here, A also goes here, no issue. Both the loop seems to work. Alright, right? What happens if I have a situation like this? Alright, you will not have 1B when you have a 3. Maybe it takes the value 1, you can have a B, you can have an A as well. A, no issue at all. The issue is only with B. Okay? A. So 1B means it goes here. This B means it goes here, no choice, right? So this B means, we are looking at this route now. This B means it comes here. A means it goes here, no choice. It falls here. You understand now? So which is right? Which loop is correct for B? Which looping is correct for B? This or this? This one, right? Now you learn where to loop. Okay? So in this scenario, this loop works. Okay? And so I bring here also. Okay? So this loop works in this problem. Okay. Certain problem, looping like this may not work. You have to loop back to the previous state. Sometimes you need to loop back to a much previous state. Okay, it depends on the language specification. You understand? So when we have to loop, we have to design whether to loop it to itself or loop back to a previous state. So looking at example, we decide looping to itself will work. Looping back to the previous state will not work. It may work for certain valid string, it may not work for certain valid string. Okay? So this is a DFM. We satisfy every state has an outgoing arrow for every input alphabet, right? And there is no redundancy. If you observe carefully, we don't have duplicate rows for an input alphabet. Okay? This becomes a DFA, and that's what you see. Okay? So let's quickly take attendance and then try to solve the exercise problem 1. Okay? You may do it very fast.